academic history. Peter did his bachelor's and master's at University of Washington before I ever arrived there. And then he went off to New Zealand to do a PhD at Victoria University. And he was able to come back to University of Washington as a postdoc while I was still a PhD student there, after another fruitful postdoc at University of Rochester. So Peter's now a research professor at University of Minnesota. He's worked extensively on Antarctic ice cores, as well as some ice cores in the North Cascades, right? In
British Columbia,
British
the
Columbia.
North Cascades.
Yeah. And he's recently really been leading the charge on getting ice cores from coastal domes in Antarctica, which I imagine we'll hear about today. It's become a running joke at every West Antarctic ice sheet workshop. We say, Peter, where should we drill to find out about that? But it's yeah, I think Peter spent a lot of time and energy pointing the community towards these really important places to drill for new ice cores. He also might be the most viral glaciologist on the internet at the moment. I'm not sure, but
viral has a bad connotation these days.
I'll just say the most popular then. Yeah, if you look up Peter's name, you'll find a video of him dropping a chunk of ice down a borehole in Antarctica and recording the sound. And yeah, he's still dealing with the fallout from his recently acquired fame on social media. So I know everybody's Googling that right now.
Yeah, I'll put up the link, don't worry.
Peter's also been a really, really active member of the community in terms of organizing the West Antarctic Ice Sheet Workshop, and did a great job this last year with the team. So we thank him for that. And yeah, Peter, I'll turn it over to you.
Thanks. That's a great introduction. Okay, can folks see my screen now? We're looking good?
Yeah.
How's that look? Okay.
Great.
Cool. Well, yeah, thanks so much for inviting me. It's really awesome to be a part of such an intensive course on the best subject, the West Antarctic ice sheet. I'm super biased because I've had a fantastic experience coming up from my undergraduate education. I've been working with ice cores, mostly from West Antarctica for that whole time, which is now a scary amount of time to me, more than a decade that I've been involved in this research. So I'll try to share with you, hopefully, a good overview of climate history for West Antarctica from ice cores. That's completely biased to my opinions and my experiences, both with field work and my scientific interest in what I'm trying to push as a project in the somewhat near future. Although COVID certainly has upended all of our plans for everything, certainly including Antarctic research. And so please interrupt me at any time. I can only see a few faces on my screen and I can't see the chat box, but please do jump in with any questions about anything. And hopefully this would be useful for what you all are thinking about with your modeling experiments, and let me know if I can help with any questions on that. So I'll just start with an overview of the major deep Antarctic ice cores all over Antarctica, and I'll spend the first maybe quarter of the talk sort of setting up the basic, really amazing things that the ice core records provide us, and then hone in on West Antarctica and really come right up to the present day in time, and talk about what we can do with waste cores to really study the processes that are affecting the ice sheet today, and that we're really concerned about for the near and ongoing future. So just to make that clear, so we'll talk about how Antarctic ice cores answer both global and regional questions about the global atmosphere and global processes in the climate system, and also regional problems like what's going on with Thwaites Glacier and Pine Island Glacier in West Antarctica. We'll come in then to West Antarctica in space and talk about what we know and don't know, the limitations of what we know about West Antarctic climate. And then my focus and what I'm trying to push for in the near future is heading for the coast of West Antarctica to gain climate perspective, where all of the change is happening, sort of running towards the fire. The driving questions in West Antarctic research from an ice core perspective, I would say all of this stuff is in my humble opinion, and I might say we a few times, which is a very royal we of all of the amazing people over many decades who've worked on ice cores in West Antarctica. So a big question that's been chased since 1980s, I would say, with ice core projects is the question, did West Antarctica collapse during the last interglacial period, the Eemian period, using Northern Hemisphere terminology, 125,000 years ago? Trying to find that recorded in deep ice in West Antarctica continues to be a challenge, and it is the focus of the next deep ice core project that the US has already funded. I'm a little bit more geared towards the question, how is anthropogenic warming emerging in West Antarctica, and gaining enough modern climate perspective in time and in space to really be able to answer that, identify the emergence of trends, answer whether or not certain warm decades are truly anomalous in the paleoclimate record. And then we're all geared towards answering the question, how sensitive will West Antarctica be, and answering that question, how much, how fast, how much sea level rise from Antarctica, how fast? That is the question that matters for people who don't study Antarctica. There are a few ways where us improving on answering that question are actually going to help folks planning, adapting our coastlines to coming sea level rise. So that's a question we need to have a good answer on, and any improvements need to come relatively soon for them to be useful for long-term planning. Okay, so on to ice cores, which is the topic that I rattle on about way too much, but I've been lucky to be really involved in this work in a hands-on way and going to the field quite a lot. So that's a big part of my experience, but a great thing about Antarctic research is that there's always a ton that you can do remotely. With remote sensing is critical to what we do in Antarctica. And of course, this modeling component, which always is paired now with these paleoclimate projects like ice cores. Modeling is something that anybody can do. You don't have to be this big polar hero going to Antarctica to learn fundamentally useful things about the continent. I just so happen to have gone there a few times, and it's a big important part of how I think about the science questions. So ice cores are really fantastic because they are these direct records of climate in the relatively recent past. So the ice core record extends back 800,000 years from today, continuously back that time. And we have layers of snow that are constantly accumulating on the ice sheet, never melting for the most part in Antarctica. And as they stack up on top of each other, you have the fernification process, this densification from fluffy snow with a lot of airspace between its beautiful the fingers of snowflakes. That airspace between the fingers of snowflakes gets compressed into ice. And so this is a video from La Dome, where I most recently was, with ice from 200 meters deep and the snow surface that it started on. Just that sort of the system that we're working on. And that is how we capture these direct samples of atmospheric gases that are almost perfectly preserved in Antarctic ice cores. So to start thinking about how we choose ice core sites, what we look for in ice core sites, I'll focus in on a place that I have a lot of experience with. It's Roosevelt Island there at the bottom of the screen on the eastern edge of the Ross Ice Shelf. And so my admission about ice core scientists is we have this one thing that we really like, and that's domes. We really like ice domes, these perfect idealized structures, a stack of ice that's accumulating. So you can think of this as West Antarctica as a whole, or a smaller ice rise where you have nice, well-behaved stratigraphy. You have some elevation that gets you above warmer temperatures down at sea level. You have a distillation of the snow as it's being transported up onto the dome, and that sort of simplifies the picture and what's preserved in the record. You don't have a lot of the noise that's down at the sides of the ice sheet. Everything's sort of idealized in that nice center, and you have your stack of layers that's not only being compressed, but also thinned by ice flow. So your depth age relationship is an exponential function. So you get exponentially older the deeper that you drill. And of course, those layers of snow and ice are like volumes of an encyclopedia, and each new page continues to accumulate as snow continues to fall. And that's a really important asset to have in Antarctica, especially where we have no past climate perspective because there's no human history on the continent and no real observations before the 1950s. So Roosevelt Island is what I would consider the classic ice dome on a smaller scale. So this is a map view. Roosevelt Island is about 60 kilometers wide. And so if we look at a radargram, so driving across the ice divide of Roosevelt Island, you see here that the surface and then this stack of layers that we call isochrones, so layers that were deposited at the same time. So you see this nice stack of layers and you see this really cool bump right in the center underneath the ice divide. And that's what we call a Raymond arch. I've talked to Charlie Raymond. He prefers an arch to a bump because he thinks a Raymond bump sounds like a disease that he doesn't want to be on the hook for. And so this is really what we look for in an ice core site, this dome structure. Having a Raymond bump under the ice divide bumps up your layers so that you have slightly older layers brought closer to the surface. So you have to drill just that much less to get some older ice. And that Raymond bump, the structure of it can actually tell you about the stability of that dome as well. And so this is sort of a checklist of things that we might look for in an ice core site. We have this a simple dome. We want to be on or near an ice divide, and if there's a Raymond arch underneath that ice divide, all the better. So we drilled through Roosevelt Island, a group led by Nancy Bertler, my PhD advisor in New Zealand, back in 2013. I guess we finished that. So we drilled about 3/4 of a kilometer. And the ice core record that we ended up with is probably about 80,000 years long. We're still puzzling over the details of it, but it's been partly published. And so this is what a deep ice core operation looks like. This tent was there over just one winter, and we did have to dig it out and remove it. So it's just a relatively light for what we would call sort of intermediate drilling, I guess. And another fundamental thing about ice cores is the snow stratigraphy that allows us to count annual layers quite a ways into the past. So for a deep ice core, a good annual layer count with decent error, we would probably get back 30 to 40,000 years. This is a mess of the various ways that we count annual layers from Roosevelt Island. So the top in blue there is Delta 18O, our water stable isotopes. It's sort of the fundamental thermometer in the snow. So it's a distillation of lighter versus heavier isotopes of oxygen or hydrogen in snowfall. And so you can see that signal's a little bit messy at Roosevelt Island, but then below that, the pinks and purples are sulfate and sulfur compounds, which seasonally are brought into the atmosphere as sea ice forms and melts. Orange is another sulfur measure. And then we have red, just the hydrogen. So this is the conductivity of the stream of water that we're sampling the way we do this in the lab. We actually have seasonal peaks in iodine relating to probably frost flowers on sea ice. Liquid conductivity, calcium is dust, and then at the bottom there in black, black carbon, which is likely brought into the atmosphere in the southern hemisphere largely from fires in Australia for where the Roosevelt Island core was. So I wanted to present this to sort of give you the basic structure of what we're working with an ice core record. Certainly, the highest fidelity paleoclimate record, possibly, arguably anywhere, but certainly in Antarctica. Just about anywhere we have annual resolution, at least going back several hundred to several thousands of years, if not tens of thousands of years. In the case of West Antarctica, the deep cores, annual layer counting back 30 to 40,000 years. I'll just give you a preview of, so one of the things I mentioned that we're always chasing in West Antarctica is that signature from the last interglacial, the Eemian period. So this is the preliminary record. It's not published from Roosevelt Island. And in red and black are just the different stable isotopes of hydrogen versus oxygen. They behave almost exactly the same, but with important differences. And so time goes from left to right here. It's just plotted against depth, but you can see where I've marked the last glacial maximum and then some warming coming out of the last glacial. The clear signal of the Antarctic cold reversal just after meltwater pulse 1A. And then a whole lot of Holocene ice. And anytime you drill in West Antarctica where snowfall is relatively high, you have a ton of Holocene ice, and your old ice is mostly in the very bottom bit of the core. But what you can see here is on the left, some interesting high values, warm values going back before the last glacial maximum that might be some preservation of older ice, potentially even Eemian ice, where the water isotope value should be as high as Holocene values or even a little bit higher. And so these are the sort of data points that are useful for model experience. And so we've been working with Nick Gollage at Victoria University to just see what different iterations of modeling you have to do to have ice preserved at Roosevelt Island during the last interglacial, even if most of West Antarctica collapses. So I may be getting a little bit ahead of myself, zooming into West Antarctica here, but I wanted to give you sort of an overview of an ice core project that I know well. And I wanted to show you what it looks like. We unfortunately don't get great samples of the rock or frozen mud beneath an ice core site always. And so in the case at Roosevelt Island, we were able to scrape around on what looked like frozen marine mud, and we got a little bit of refrozen mud on the back sides of our cutters that you can see there in that picture. So we got little samples that Reed Shearer has been able to look at and try to identify based on the diatoms and things that are in there. But from what I understand now, it's been pretty difficult, and our samples are literally just scrapings, so pretty slim pickings. Okay, and I wanted to go quickly to one or two more sites as an overview, and I'm already conscious that I'm taking more time than I intended, so I'll try not to continue doing that. But another site that's really crucial for what to sort of illustrate what we do with ice cores is Law Dome, and this is where I've most recently been in Antarctica in the 2018-19 season. I didn't do this work, but this is why Law Dome is so important. It's really the keystone record of human-caused greenhouse gas emissions that documents the huge input of CO2 and methane and other greenhouse gases into the atmosphere after the Industrial Revolution. So these plots show data that was published in 1996, 1998, and I've updated it with these red dots for our current levels of methane and carbon dioxide in the atmosphere. So this rapid anthropogenic input of greenhouse gases, that huge control knob on the climate system, and we're watching the entire Earth warm up in response to that extra trapped heat that these gases absorb in the atmosphere. And so this is an archive that we go back to answer further questions about the most recent past, the last couple hundred years to thousands of years. And just to show you what that looks like, we went back in 2018, 2019 to take large volume samples to study really detailed processes, not only about how greenhouse gases get into the atmosphere, but the removal processes. So we're studying oxidation in the atmosphere at that site. And so that's sort of more the globally relevant questions that we can answer with Antarctic ice cores. And the last sort of overview is just looking at the three deepest ice cores in Antarctica. So Dome Sea, Waste Divide, and Vostok, the deepest and two of the oldest ice cores in Antarctica. So just a sense of scale of these projects are really massive undertakings. You're drilling for 5 or 6 years every summer to recover more than 2 miles of ice. And what I'll show next is actually a combination of the Dome Sea and Vostok records, our two oldest records in Antarctica, that really give us the highest and the most direct picture of CO2 and other greenhouse gases in the past over the last 800,000 years to today. And to get today's CO2 on that plot, we actually have to adjust things a bit to get such a high value on there. So you can see just how rapidly we've changed the game from the past natural fluctuations over the ice ages to our human input of greenhouse gases. And the great thing with ice cores is, of course, we also have this proxy for temperature, the water stable isotopes, it's not as direct as the greenhouse gas measurements, that air trapped in bubbles, but it's deposited in the same place. And you obviously can see that the tight relationship between greenhouse gases and temperature. And this is, I wanted to show, this is sort of the most important achievement for the ice core community, I would say. But it also highlights why we are constantly looking for Eemian ice from that last warm period in West Antarctica. And it's because if you look at that blue plot, the temperatures during the Eemian were a couple of degrees warmer than they are today. And so this is considered our closest analog to where we're headed in the next century or so. And a big concern there is that there's a couple extra meters of sea level that were present during the Eemian that we don't know exactly where they came from. And all signs are pointing to it being West Antarctica. So it's another big test for modeling experience to figure out how West Antarctica responds in that situation. And please, I'll remind you again, if you have any questions, feel free to jump in. And so I highlight this record now because, or the Eemian now, because again, it was a goal of the Waste Divide Ice Core project, which was the last truly deep US ice core project in central West Antarctica. So this was drilling from 2006 to 2013. I was there 2009, 2010. It was my first trip to Antarctica. This was intended to be, drilling into the deepest part of West Antarctica, the Bentley subglacial trench, and there should be 100,000-year-old ice down there. The record ended up being only 68,000 years long because of the anomalous warmth, the geothermal heat at the bottom of waste at this site. So all of that extra 40,000 years of ice that we were hoping was there had been melted away, which is a real bummer if you're looking for the Eemian. But the advantage there is that in that same 2-mile thick stack of ice where you thought you were going to have 100,000 years, you have 68,000 years that are much thicker. And so the Waste Divide Ice Core, I think, will always be our highest resolution paleoclimate record going from the last glacial to today, which is obviously a really important major climate transition to have at the highest resolution possible. This is sort of a crazy plot from our big result of the temperature record, the water stable isotope record from WASTE. So in the center of that plot is the purple and yellow line. That's the Waste Divide Ice Core. You can see that all, 9 records from the major Antarctic ice cores at that point are broadly the same. So coming out of the last glacial from left to right, warming up with an Antarctic cold reversal of various severity at all these different locations. But importantly, when it's gratifying to see, right? We go to all these different places, and of course the last glacial transition is roughly the same, but there are important differences. And one of the differences that we saw at Waste Divide was that the warming there out of the last glacial started about 2,000 years earlier than it did for much of the rest of Antarctica. So by 20,000 years, we were starting to warm out of the last the glacial maximum. Whereas if you look at the lines just below the Waste Divide curve there, you can see it took another 2,000 years for the rest of Antarctica to start changing. And so that's an important difference that we were able to look into with some specificity. And the high resolution greenhouse gas records from Waste Divide are also crucial. So I won't dwell on this that long, but we have sub-century level measures of CO2 concentration coming out of the last glacial. So you see these pulsed increases of CO2 in the curve with the blue dots that add structure to the way that greenhouse gases changed coming out of that last big natural climate transition. So really a fantastic record, and it is the conditions at Waste Divide are really similar to a lot of the deep ice cores in Greenland, and so it's a really great sister site between the hemispheres to look at how both of the hemispheres respond and lead and lag on these big rapid climate events. Okay, so that's sort of all that I want to say about sort of the bigger, deeper time perspective, and now I want to look a little bit more closely about at WASTE and its climate setting. And so I'll do that with a video of a year of precipitation in the MERA reanalysis. So this is a modeled version of observations that this is for the year 2017 that Jan Lennartz, who's at Boulder, put together. So the red, of course, is the wettest air masses. And what you can see is this circle of the circumpolar westerly winds. So westerly meaning it's moving from west to east. And then because of the Coriolis force, as those storm systems come into the continent, they continue to curl, and you actually have easterly winds on near shore of Antarctica. So if you focus on, I'm sorry, my pointer is terrible in Keynote. So can you see my mouse?
We can see it.
Okay, great. So if you look at where Pine Island Glacier and Thwaites Glacier are, and this coastline that we know is changing rapidly, you can see that the storms really crash in here. In general, you have a low pressure system that's spinning storms. So we have the Amundsen Sea low, we call it. And then you have high pressure that gets stuck here in the Drake Passage. And so those two systems tend to funnel moisture at the Pacific coastline of West Antarctica. And that's really why I find this part of Antarctica so fascinating. And it has really a lot of analogs to the way that the Pacific Ocean interacts with Western North America as well. It's the direction of moisture transport is from the Pacific Ocean into West Antarctica, and that's the largest pathway for moisture to come into Antarctica, period. And this is the second reason why WAIS is a marine ice sheet. So not only is it because it's grounded below sea level and it's subject to this marine ice sheet instability, that's really, really important, but its surface mass balance, all of the surface processes, how West Antarctica forms and is sustained is through marine air masses coming off the Pacific Ocean. That's super important. And those marine air masses are also where warmth is entering the continent. And those same air masses are what bring snowfall all the way up across the West Antarctic Divide into the Ross Sea system and up to the South Pole and into East Antarctica. So West Antarctica is really this marine gateway for moisture and energy to enter all of inland Antarctica. You can see that as well if we just plot, this is accumulation rate over the entire continent. So the lighter colors, yellows, are high snowfall and the blues are low snowfall. So of course, most of Antarctica gets almost no snowfall. West Antarctica and the Pacific coastline of West Antarctica is super, super wet. So the yellows here get up to a meter of accumulation per year and beyond. And West Antarctica is really unique for how deep inland those high accumulation rates penetrate. And I guess I find that looking at these maps of accumulation rate sort of belies the direction of transport. So you always have a windward and a leeward side of any orographic barrier that's going to cause most of your precipitation to drop where it first hits that barrier and starts to rise and cool. And so you see those really high accumulation rates along the Pacific coastline of West Antarctica. And you can also see, like, against the Transantarctic Mountains, if you look just south of the Ross Ice Shelf there, you see higher snow accumulation rates on that west side of the Transantarctic Mountains. And that's telling you that that's the direction of moisture transport as well. So moisture coming into Antarctica from the Pacific via West Antarctica is a super crucial process and one that I don't think is appreciated enough, hence me harping on it. Okay, so again, focusing, I guess, on the major players here. So the Amundsen Sea, Bellingshausen Sea, both of them are home to the Amundsen Sea low, the Bellingshausen high pressure systems. Those work together to shoot moisture at Pine Island and Thwaites Glacier. And of course, we care about those glaciers so much because they are how West Antarctica is shedding so much mass, and they are particularly unstable and large. I don't think I need to rehash this after, I think you're probably talking about this every single day in a course like this.
Yep.
The marine geometry of West Antarctica's bed and the way that winds are promoting the upwelling of relatively warm water underneath ice shelves, melting them from below. And you can see that in fantastic new remotely sensed data sets that we're getting. This is the latest update of ICESat and ICESat-2 surface elevation change. So reds are a lowering of the ice sheet surface, which implies certainly along the West Antarctic coast, increased flow and loss of ice at the ice shelves. And so again, I don't think we need to harp on this, but this is really the part of West Antarctica that's changing now. And so it's why I sort of focused in on what can ice cores bring better understanding to for the processes that are at play in this ice ocean atmosphere problem with marine ice sheet instability and Thwaites Glacier. And just another way of looking at this is if we track the mass change from individual drainage systems, the biggest losers are all in West Antarctica. I think it's one of the systems that's changing the most in the positive is also the CAM ice stream shutdown is holding back a lot of ice in central West Antarctica, but along the coast, Thwaites and Pine Island are losing a ton of mass, so contributing up to millimeters to sea level, which doesn't sound that much, but over the entire planet, obviously, is very significant. And so this also has East Antarctic players there, but nobody can match how much ice West Antarctica is shedding, and it's sustained and it's accelerating. That's concerning.
Peter, can you just point out the CAM and Willans and Mercer?
Yeah, sorry, and I'm just, my mouse like sometimes works and sometimes doesn't. Good?
Yeah.
So in green, you can see the increase and so I love these surface elevation change maps because there's so many processes that are highlighted. And so one of them is this big blue bump here. All of this ice is stuck because this ice stream has essentially shut down something like 150 years ago. And so all of this ice used to be streaming through on a deformable bed, or I'm not an ice stream expert, but for whatever reason, the CAM ice stream shut down, and it's right near one of the deep ice core sites on Sipel Dome. That's was the previous place before Waste Divide that the ice core community tried to find that Eemian ice. Didn't find it there, didn't find it here. Now we're going to try to find it here. You can just keep digging. Cool. Yeah, thanks for that, Trevor. That's a really cool process that's highlighted there. Another way you can see that it's really ice shelves that are losing mass to the ocean is that the thinning is here in the fast flowing outlet glaciers that flow into ice shelves, but the nearby coastal domes, which are the places that I care a lot about, are either not thinning or not thinning as much as the ice shelves right next to them. And so that tells you that they're not connected to the same process that's causing this increased ice flow and a lowering of the ice surface right next to them. Super cool. There's like having these data sets just has unlocked so much understanding. But what we can't do in Antarctica, let's see if I get my mouse back in the right spot, is really capture climate in time and in space well. And so climate perspective on wastes, and particularly the ice ocean atmosphere change, is fundamentally limited in time and space. And this is like the classic problem in studying climate in Antarctica, and especially West Antarctica, is that our observational record is too short to get at these long, slow changes, like what part of the Thwaites and Pine Island situation is still related to them coming out of the last glacial maximum. How is there any anthropogenic signal to what's going on there? How does the Pacific Ocean with its multi-decadal variability play in? If we only have 50 years of weather observations from one place in West Antarctica, we're not equipped to answer those questions with any statistical rigor. We can try to use models to extend those the weather and climate perspectives, but those are not pinned down by any observational constraints. So that's where the ice core record is really most powerful. And so this is from that paper that I wrote with Eric Steig, who I would consider my biggest mentor and supporter, and a great partner in research. So the ice core record here is a stacked record of cores that we have across West Antarctica. I'll show you more about those. But just illustrating that we get much more time perspective from them than weather station. So this is the bird station temperature record beginning in 1957. So with the International Geophysical Year, that's when science essentially begins all across Antarctica. Climate reanalyses are these model assimilations of all of our spatial and temporal observations globally. They are really great. They're a fantastic tool that we absolutely rely on for everything in like global climate. but they are only good back to the beginning of the satellite era when our spatial and temporal coverage increases dramatically. And especially in Antarctica, if you try to correlate climate reanalysis data, they do go back before 1979, but if you try to look at how well they match the few station observations that they do a terrible job before 1979. So we have to move forward with those. And then of course, our records of that ice loss really only began in the 1990s. So my question is always with those big, we're shedding all that mass. What were those curves doing in that time before 1990? Are we just starting this change and this great ice loss? Or how much variability is there going back in time? And those are questions that are hard to ask unless maybe we can find some part of the ice core record that can really tell us about processes that are driving that mass loss. And that's what I'm really most interested in. So I was already hinting at this. Modern waste climate, our record from observations is Bird Station. It was established in the late 1950s. It's good that we have it, but it's not enough. So thankfully, the Bird Station represents all of inland Antarctica quite well based on what the reanalysis and the models say, which are also flawed. So this is a map showing the spatial correlation of the record at Bird Station with the records across Antarctica. And so the red indicates that it's a good match with that area. So all of Central West Antarctica, you start to lose a little bit of correlation getting out to the coasts. The models that's correlating with, though, are going to be really low resolution for topography. So I would argue that there's probably not capturing the coastal dynamics well enough at all. And of course, this being the planet that we live on, the Bird Station record is warming at one of the fastest rates on the planet. So 2.2 degrees Celsius of warming from 1958 to 2010. That's it's not enough to really change surface processes in Antarctica yet, but as surface melt on ice shelves becomes more of a problem, it certainly will be a new factor that needs to be considered. So I'm honing in here on what I think about a lot now. And so again, I'll sort of illustrate the fundamental challenge of Antarctic climate is that we're limited in observations in time and in space. So this is just a super rough sketch, but if we have our stations, like Bird Station covers this time from say 1960 to present, and it's pretty much continuous. It has some gaps in it. And so that covers, point locations at all these stations, largely on the coast. Thankfully, Bird Station was quite far inland because the US was crazy in the 1950s. We've added to that automatic weather stations starting, roughly in the 1980s. So these little dots then further spatial coverage around the continent that's now continuous beginning at that time when the first ones were set out. We have satellites that give us spatial coverage of the entire continent. They're of course not directly tied to what's actually happening at the surface. So there's some really important surface validation you need to do with satellite records, but they're spatially continuous, which is you're covering all of that spatial area. And so what ice cores add to this is we're the only people who can start from today and go back in the past and essentially get weather station level data, especially over the last few centuries, but covering that whole time. And we can do it in a number of places if we get out to enough places. And that was what the ITAS array did from 1999 to 2002 in West Antarctica. The US ran these traverses that were taking ice cores and surface observations and radar measurements across the West Antarctic ice sheet and all over Antarctica. It was an international project. And there are a number of these that were 200 years long. And this is really our first and only picture of modern spatial climate in West Antarctica that we can tie to the Bird Station record and other reanalysis records. Sort of a kicker of what we found looking at the water stable isotopes, the temperature records from these cores. So this is over the last 2,000 years. This actually is mostly the waste divide record going back 2,000 years. But you see this decreasing trend that's actually due to orbital forcings that are promoting a little bit of cooling. But we were trying to see how anomalous the warmth that was observed in West Antarctica in the 1990s was relative to the deeper paleoclimate record. And because we now had this spatial network of cores and the waste divide core that goes back so much further in time, we could say that the 1990s warm anomaly is likely to occur it has only occurred 2 times in the last 2,000 years. And because we didn't have enough records that covered that entire period, we couldn't say with enough statistical rigor that it was truly anomalous outside the bounds of natural variability, but it was really, really close. It was like close enough that we got published in Nature Geoscience, but not significant enough that we got published in Nature, which is a silly way to reference it, but it's the reality of scientific publishing. Okay, so I'll try to go quickly now, and I might skip a few slides because I classically have way too much information, but hopefully this is some interesting new stuff, looking out at places where nobody's been to try to fully cover climate in space in West Antarctica, really get out so that we know all of what's going on in all of West Antarctica. So we know the Pacific sector is changing rapidly. You guys are talking about that every day. The change is focused at the ice-ocean atmosphere interface. So why aren't we there is the question that I peskily am asking. We don't have any data directly from this entire coastline from Thwaites Glacier around to the Ross Sea. And I think we need to fix that. So for the rest of the talk, I'll focus in on ice domes in the vicinity of the Getz ice shelf, an ice shelf that's thinning rapidly, that we've never done any ground-based studies except for in the last year or two. And all of these ice domes, there have been no ground-based science ever. And this logistically, it's because this place is really far from any research station, and the weather is historically bad because of how the storms all crash in off the Pacific Ocean. So this is our picture of West Antarctica. I'm sorry, I've rotated us. And I want to just impress upon you how big of a space this is. So this is pretty much to scale. I've stretched this on here and made sure that the scale was roughly correct. So the red dots are ice cores. You can think of them like weather observations, weather stations. And so along the entire coastline, the length of the Western US, we have a station, say on the Olympic Peninsula of Washington, and we have one in San Diego. That's insane. And this is where all of the ice loss is happening. So here the blue dots are the deeper cores. So, this is our spatial and temporal coverage of climate in West Antarctica. We've got, temporal coverage going back far into the past, tens of thousands of years is great for central West Antarctica. I think that's all we need for the inland portions of the ice sheet, the bigger ice sheet processes. But looking at the complex ice-ocean atmosphere interactions at the coast, we need to do better. And another way of looking at this, if you stay with me on the analogy of the west coast of the US, is if we care about the weather and what's going on in San Francisco, is it okay to only have observations in Reno, Nevada? So this is a transect of elevation from San Francisco to Reno. That's of course the direction of moisture transport from the Pacific Ocean, the way the jet stream works. And if we put that to scale with the same elevation transect in West Antarctica from Thwaites Glacier to Waste Divide to Bird Station, where we actually have that weather station that began in the 1950s, that's what we're looking at. So the orography, the mountains are a little bit different, but it's similar. We care about these coastal processes, but we only have observations on the far side of this big orographic barrier that's modifying our air mass. So I'm arguing that that information from Bird Station is great, and it's really, really fundamental to have those observations, but they're not tied to the processes that are happening at sea level right at the front of Thwaites Glacier. And we have places to get ice cores right there. It's my simple argument. Could sort of end my TED talk right there. So again, you've probably seen diagrams like this for Thwaites Glacier. It's a really complex interaction of ice dynamics, ocean dynamics, upwelling, and then the atmosphere is really modifying those ocean dynamics. So the winds drive circumpolar deep water beneath the ice shelves. That's tied to Pacific Ocean variability. There's some evidence that the westerly winds might be strengthening, and that might be caused by humans, but we don't have observations to constrain that. That's a model-based observation that was made last year. I think we can test that with ice cores from out there. I might go through this quickly, but just this is a plot that I look at these sort of plots all the time. So this is showing spatial correlations between sea surface temperatures in the tropical Pacific and the structure of the atmosphere. So when you have high sea surface temperatures in the central Pacific, it drives anomalously high pressure off the coast of West Antarctica. That affects the winds. And so this time series plot from 1975 to 2015 shows how tightly locked sea surface temperature in the Pacific is with the winds offshore of the Amundsen Sea coast, where the Thwaites Glacier and Pine Island Glacier are. And so this is sort of the spatial connection between the Central Pacific and West Antarctica is a really important and unique thing for Antarctica. And so that's what's been pointed out by a number of folks now. And it's been suggested that all of those processes are tied to this trend in the westerly winds. This is a plot from 1920 to 2020 of increasing westerly winds. Those are model generated, so they're not tied to observations in a sufficient way. And so that's what I think we can test by going out to the coast. So the wind forcing for the geometry of what's going on at Thwaites Glacier and other ice shelves out there, the winds are really key to the ocean circulation, bringing warm water onto the ice shelves. So I'll go back to this ice dome picture. And so not only do we have these central ice domes, like the interior of West Antarctica, the continent is ringed by these smaller coastal ice domes like Roosevelt Island. And we have fantastic coastal domes out on the Amundsen Sea, thankfully. Unfortunately, they're way out on the Amundsen Sea, so they're quite hard to get to. But this is what I've been trying to steer our research community towards. So these are our ice domes that are within the Getz ice shelf out there just west of Thwaites Glacier. And I think these are places that we could get ice cores. I don't think we need ice cores at all of these, but they're all just fantastically interesting to look at based on the limited data that we do have and ways to explore them. And so just this is a time lapse of visible satellite images just to show you how close these sites are to the ocean dynamics that are driving ice ocean atmosphere interactions out there. So you're literally, I mean, sometimes less than 5 kilometers from the ocean, which can be really tricky and make for complex ice core records, but we can get ice core records from these sites. I first got excited about these, seeing data from NASA's Operation Icebridge campaign, which flew airborne radars over the coast of West Antarctica from 2010 until 2018. So this shows ice thickness at these domes. So some of them are up to 800 meters thick right on the Amundsen Sea coast. So it would be quite an undertaking to drill all of that ice. That would be probably 5,000 to 10,000 years of ice safely. But again, you're potentially freezing really old ice at the bottom of these ice domes because the ice isn't very thick. The ice at the bed should be totally frozen and not melting. So you could have very old ice at the bed of these, but the practicalities of getting that ice are quite extreme. So I sort of just want to highlight how interesting these places are and wrap up here. But this is a flight over one of the ice rises. In these old images from the 1960s, you can actually really see the structure of the domes really nicely and this clear ridge on the surface. And we now have flights over these domes with radar, high frequency radar, that can see into the surface layering of them. And so we can actually start to build ice core records, quote unquote, without ever going there on the ground. So this radargram shows, 5 years of annual layer thickness over this right island, which nobody has ever gone to, probably never will in the next 10 to 20 years. But what Julia is going to be doing is picking these annual layers and examining that time series that you get in snow accumulation from that site, and doing this all across West Antarctica to see how snow accumulation is preserved at all of these places. And that's important beyond just getting snow accumulation rates at these places where we've never measured it on the ground. You also get a time series of snow accumulation, and year-to-year variability in that amount of snowfall is controlled by the structure of the atmosphere and what those low and high pressure systems are doing. And so that's important, really new information that we've never had with ground constraints, right? We have models and climate reanalyses that get at it fairly well, but we don't have the direct observations like these are going to provide us. If we look at a larger picture across an entire ice dome, so this is Cycle Island, we can zoom in near the surface and we see this little bump of the isochrones underneath the ice divide, which is possibly a surface accumulation feature, but it could also be a Raymond arch, which is that feature that indicates long-term stability of an ice dome and nicely brings older layers that much closer to the surface. Folks like Brooke Medley at NASA are starting to get to do some of the layer picking on these domes. And so flying across the ice domes, you see the variability in snow accumulation. So the black line there is the elevation of the ice rise. Blue is the accumulation rate. You can see how variable in space the accumulation rate is. And that's just based on wind redistribution and surface topography. Little bumps and concavities promote either deposition or erosion of the surface snow. And then across the ice divide, you can see that on the left there, you're on the windward side that has accumulation rates of up to 1.4 meters per year. That's a lot for Antarctica. That's like 10 times average for Antarctica. And then going on to the leeward side, you're in a rain shadow. So you get very little snowfall, or very little for the Amundsen Sea coast is like 0.5 meter per year. The green line there is what a lower resolution model is saying happens across those domes. So you can see that the models are doing remarkably well for having no observations to constrain them, or at least no ground observations, but they generally are getting some of the picture right. So we can now start to constrain these things even without getting ice cores, but ice cores are going to give us that much more information. One of the last things I want to do is focus in on this really beautiful ice dome, Martin Peninsula. It has what we call a double divide structure on its ridge, where not only does it have this ridge where the ice is accumulating right on the central divide, there's sort of depressions on either side that make this double divide that you can see in visible satellite images and this DEM. That structure only forms after quite a long time. And so we have this way of thinking about accumulations of ice. It's called the characteristic timescale T. It's the thickness divided by the accumulation rate. Because of Operation Icebridge, we know the ice thickness from radar, and we have a constraint on the accumulation rate. So the characteristic timescale of a 450 meter thick ice rise that has a meter per year of snowfall is 450 years. Is sort of the turnover time for any big perturbation to sort of come through the system. That's my non-glaciologist explanation of that. So these double divide structures based on modeling only form after 4 times that characteristic timescale. And so again, without ever having gone to the ground, nobody's ever been to Martin Peninsula, but we can already say that, well, having that surface feature, this is the model that sort of shows how it forms. Having that feature there suggests that it's been stable for 4 times that characteristic timescale, which is about 1,800 years. And so these are the things that we're starting to learn and explore at these places and help use to justify why we want to go learn more. Okay, so just wrapping up, this is me describing my manifesto and the next probably the lifetime of my research to try to get it out to these places, especially after COVID. But these are high snowfall sites, which is sometimes looked down upon for ice cores because that means you're preserving less time at depth. But it makes for high resolution. A thick package per year means you can do that much more with the samples that we get every year. So high resolution records, 100 to 200 meters deep is what I'm interested in. And that gives us, I mean, it's almost 1-to-1 depth with age at these places, but 100 to 500 year records drilling that deep. That's something that we can do in a matter of a week or 2 if we can get out to the site. The drilling is really simple. We're not proposing to do anything with the ice while we're there. We just sort of a smash and grab, get the ice and get it home so that we can then run the full suite of chemistry on the snow and get records of sea ice, polynya conditions, and then records from winds in a number of different ways, and also validate those snow accumulation rates that we get from airborne radar with real annual air counting in an ice core that has multiple ways that we have that annual signal. Okay, and again, I guess I was highlighting that some of these features, the dome structure that you can see clearly in the DEMs, the ice divides you can see in aerial photos and these DEMs as well, and then suggestions of Raymond arches either directly from radar grams or from those surface expressions that suggest a Raymond arch and that long-term stability of ice rises is there. So that's a little flavor of where I'm trying to push us to really know better what's going on right at the ice ocean atmosphere interface. So I hope I've given you a broad overview of what we do with ice cores in Antarctica generally, and then how we hone in on West Antarctica and where we're going now in the future. So I hope we'll put a dot out here sometime in the next 5 or 10 years. And the US community is going to be drilling a deep ice core at Hercules Dome, a place that if West Antarctica collapsed during the last interglacial would be beachfront property. And so the idea is that not only have they have pretty good radar data now that suggests the old ice is there and it's nice and flat, right? The deeper layers in the ice sheet tend to be folded and out of sequence, but these look good. And some really interesting modeling that Eric Steig and others have done. Climate modeling, if you collapse the West Antarctic ice sheet, suggests that the signatures of what that change means for climate in West Antarctica and a real clear indication that the ice sheet has collapsed, it should really be preserved there at Hercules Dome. So it's an exciting project. It's a big undertaking to get that deep ice, but that'll be something to watch over the next, 5 to 10 years for a project like that. So these things don't move quickly. I hope that I can move a little more quickly by wanting to run out to the Amundsen Sea coast and grab cores to really bring our perspective right out there to where we see the change. Okay, so I'll leave us on these driving questions. I hope I gave a good overview of this, and we have half an hour to chat before I have my first parent-teacher conference for my 10-month-old daughter at daycare.
What?
Just checking in, letting us know.
It takes a few years to get into a good daycare in the Twin Cities, that's for sure. Got to start interviewing early.
We had quite a time finding a spot for her this year.
Well, Peter,
cool. Okay, let's see. I'll stop sharing right now, maybe, just so I can see people better.
This is a really fantastic seminar. I think any research priorities that I myself have for West Antarctica, they're just gone. They're obliterated by your persuasive manifesto, as you said.
All right, that's what I want to hear. Let's see. Can you guys still see my keynote there?
We can, yes.
Okay, good, because I can see all of your faces now, so we're good to go.
So, good morning, students. What's on your mind after that energized look at the ice sheet and the young end of the history?
I was wondering, you talked about Law Dome and how it was a keystone in the record of anthropogenic input. Why is that so?
Why Law Dome?
Yes.
Yeah, it's because as it has become somehow my expertise, it's going to the snowiest sites in Antarctica, and so Law Dome is really important. My screen sharing is still really weird here. Let me stop real quick here. I'll bring it down. I've got 2 monitors going on, and it just doesn't make it easy. So I'll share again here. And I just wanted to show where we are here. Maybe we'll go back to that accumulation map. So can you see that?
Yes, we can see it.
So Law Dome is over here. And you can see it's split. It's sort of green and yellow. And so it has this huge snow accumulation gradient across it because as the winds come around, the storms curl in and they crash on the far side of Law Dome. And that's where we have this at the high accumulation site called DEO8. And it's where we went in 2018-19. And it's because it has such massive snowfall, it locks in the gases at really high resolution and super quickly. So the gases there, right, the close off process between surface snow and ice takes anywhere between 50 meters and 100 meters to fully lock off and isolate an air bubble from the atmosphere. And so over that time, the fern column is actually mixed with the atmosphere. There's some diffusion that starts to happen, but Laudome traps gases really fast. So if you went to a place like Vostok or even Waste Divide, it's going to take a couple hundred years to lock in that air. So you're not actually going to have preserved that 100, 150 years ago when that big change happened. It's not going to be recorded there yet. So Laudome is the one place where that, I don't know what a good analogy for it, but the recording process is much quicker at Laudome because it just has prodigious snowfall. And I don't know why exactly it maintains a relatively low temperature for where it is right on the coast too. I guess it has some connectivity with the inland East Antarctica. So the mean annual temperature is like minus 19 degrees Celsius. And so that we sort of consider minus 20 Celsius a good cutoff before the gases start to play around a little bit and escape and mix. Some chemistry starts to happen when the ice gets a little bit warmer. So yeah, it's this fantastic archive.
Thanks.
On the same topic of Laudome.
Oh, sorry, Hannah, go ahead.
Oh, sorry. On the same topic though, I was wondering if you could explain, I think you mentioned that you guys were trying to pull CO2 out of the atmosphere via oxidation or something. Is that right?
Yeah, this is my postdoc work with Vas Petrenko, who's at the University of Rochester. We were studying the oxidation process that it's not so much connected to CO2 in the atmosphere, but it's the main removal process in the atmosphere for methane. So this oxidation, it's the main oxidant in the atmosphere is hydroxyl. It's super duper reactive, hence why it's the main oxidant. So we can't measure it directly. It's like, a hydroxyl molecule has a lifetime less than a second. They're constantly changing all the time. So we have a tracer that sort of integrates the signal, and that's carbon-14 of carbon monoxide, which is an insanely difficult thing to measure in ice. I don't recommend it. I wish I never did it. But Voss figured it out, and I was the poor sucker that executed it. And we have a fantastic record now from the 1870s to today. We had to go to Laudome to do it again because the snowfall not only preserves those gases so well and so quickly, but it also shields them at depth rapidly. So because we're measuring carbon-14, the cosmic ray flux is going to continue to be bombarding that ice, and it produces extra carbon-14 in the ice as the gases are sitting there. So we need that burial to shield the ice as fast as possible. And Laudome is literally the only place on the planet where we could do a reconstruction like that. So
So cool.
I could talk about it. It was a very traumatic experience. It was a really hard project. We were out, I was running a camp of sort of 7 or 8 of us for something like 80 days. And we sampled 1,000 meters of ice over 6 different boreholes because we're measuring this teeny tiny component of the atmosphere, carbon-14 of carbon monoxide. There's like 4 kilos of it in the entire atmosphere. And to get enough of it for one sample, we needed a grand piano's worth of ice. And we had to not only drill it, we had to melt it and pull the gas out of it there in the snowiest place on the coast of East Antarctica. And I had to build the thing that we did that with, and I was the only person who knew how to use it. And yeah, we do really crazy things to try to better learn how atmospheric chemistry works, right? Like again, and the story with ice cores is like we see these processes that are untested in global climate models, say. So right, all global climate models that have the radiative forcings, your global energy budget, they need to have their greenhouse gases in the atmosphere, and then they have this control knob is the oxidation. How quickly is methane removed from the atmosphere? We have zero constraints on that process besides what chemical equations and rough numbers suggest. It's a really big dial on a methane molecule, right? They're a number of times more potent of a greenhouse gas than CO2. And thankfully, because of that oxidation process, they only stay in the atmosphere for 10 years on average. But you can imagine, as we've rapidly changed the atmosphere over the last 150 years, that might produce more or less of that oxidant. And we don't have a record of that. and hopefully now from Law Dome we will. And thankfully our timing of the project got this massive field work done, got all of our lab work done all before COVID hit. So we have all of our data and we're in a pretty safe interpretation phase. So that's worked out nicely. Yeah, sorry, that's another story, but still coastal Antarctic ice cores. It's my jam.
What a labor that was.
Yeah, you can. I guess I share about it a lot on social media because it helps me process the
what you're going through.
Really, really fantastic project. I mean, it couldn't have gone off better with better people. So I'm joking, but it's a right. All of this work, especially these big like ice core projects, tend to be sort of a slow burn. They take a long time. I've been to Antarctica once every 3 years on the clock for the last 10 years now, and that's sort of the research cycle. It was first time for my master's and the second time for my PhD and then for my postdoc, and then my postdoc was long enough that I went again for my postdoc. So yeah, these are really long, and it ends up being a significant event in your life too. You know, a lot of time away from home and equal amount of time locked in a basement lab handling samples that you don't want to mess up.
Peter, I just want to thank you for a really great, interesting talk. I have to run to get a GSA session ready. But
no worries. Thanks, Eric.
Thanks very much.
Take care.
Okay, you too.
I have a question about whether ice has been looked at as like a natural analog for like storing carbon dioxide. Is that at all something that people have been trying to kind of work with, or is it too long of a time scale to really be possible?
I mean, I don't know much about that, and I haven't heard a lot about it. My reaction would be that it's not. I mean, especially going into a warmer and warmer world, ice is not the place that I want to be investing much of anything. I mean, I do think folks have calculated how much carbon is locked up in the ice sheets, right? Like that's a fairly simple back of the envelope calculation based on the concentrations and the volume of ice. And 10% of the ice in Antarctica is that air, that old air. Yeah, I would put my CO2 in rock. That sounds better to me, but I don't honestly know a whole lot about that. But it reminds me of all these crazy ideas like storing nuclear waste in Antarctica, right? Like in the past, Antarctica was sort of seen as this big ice box where we could like store all of our problems. And thankfully, you know, the Antarctic Treaty came around and people thought better of that. But similar, I mean, yeah, so yeah, that's an interesting idea about storing CO2 there. Or there are other thought experiments that folks do. Like I think of the group at Potsdam where they have all these wild ideas like, well, what if we sprayed seawater onto the ice sheet and built up structures in the ice that prevented some of these runaway processes? I mean, these are papers that are out there that you can look at. They're fantastically interesting thought experiments, but then if you start looking at the practicalities of the energy and the resources required to pump seawater up onto the continent to build it, I think the idea is that you're going to build up the elevation so that it gets more snowfall so that it builds itself up. But it's an interesting end of geoengineering, but geoengineering in general terrifies me because I think we should know by now that there's a fair amount of hubris involved in our relationship with nature and what we think we can or can't do. I don't think we have a lot of room for that these days.
That reminds me of the idea to construct a pinning point under Thwaites.
Yeah, I was thinking about that too. I didn't say it, but yeah,
Yep.
Right. It's like a number, like tens or hundreds of Panama Canals worth of material you'd have to put underneath Thwaites Glacier. But I mean, I like it as it's a more targeted. Like I don't think the negative consequences from building a massive dike underneath Thwaites Glacier would be as large as like shooting sulfur into the atmosphere